Finally, we're at the point where we're going to take the metal oxide semiconductor connection and actually turn it into a useful device. And the first lecture we're going to do about MOSFETs is going to be how they're constructed, and then the second one, the one that comes after this, will be kind of how they work. And neither one of them is very long, so they're not as long as the two that we just covered. When we make a MOSFET, we have some kind of substrate, and we're going to talk about the P-type material substrate. It could be N-type, but we're going to start out with P-type. And then there are two areas of heavily doped N-type material, and there's going to be some kind of distance between them. So the width of the device is actually the front to back distance, and then the length is the distance between those two areas of heavy doping. And those two parameters, the width and the length, actually are parameters that are used frequently in designing MOSFETs. Then there is an oxide that is put on top between the N-type areas, and then on top of that is metal, and there is metal on top of the oxide. That's just like the metal oxide semiconductor connection there in the middle, and then to either side there's also a piece of metal that is on top of the N regions and also a piece at the bottom. And then there are terminals connected to each one of them. The terminal at the top, the S, is called the source, the G is the gate, the D is the drain, and the B at the bottom is the body. So we have source, we have gate, we have drain, and then we have body. And most of the time, the body connection, most of the time we won't see that or use it. So that will be just something that we'll talk about why it's there in a bit. So the terminals, drain, gate, and source, those are the ones that we use the most often. And all the current flows between the drain and the source. Nothing flows into the gate. There is a voltage potential at the gate. That's just like the voltage we talked about in the previous MOS capacitor and metal semiconductor function lectures. So there is a voltage there, but there is not any current that flows into the gate. There are two types or versions that you can make depending on substrate. So there is a P channel or PMOS, and that's where the heavily doped areas are P areas on an N-type substrate, and then the N channel is the one that we looked at in the previous example. They both work the same way, but they have opposite voltage and current characteristics. So we're going to look at a cross-sectional view now, and that means the width is no longer visible, so the width actually goes into the page. So that's where the width is. It's not visible, but that's what one is talking about when one talks about the width. There is a length between the two areas, and then we will start talking about what happens. You will notice the source and the drain look exactly the same. There is the same kind of doping underneath them. You have the same kind of contacts, and technically, you could use this either way, except there's a reason why you actually can't usually, and that has to do with the body connection occurring inside the device. But in any case, right now they're completely the same. The gate is isolated from the semiconductor through the silicon dioxide layer with a thickness, which we talked about before, and there is no current, again, flowing into the gate, but there is a voltage. So the fact that there's insulating material there in the silicon dioxide layer prevents any current from going in there. So there is not any current flowing, but there is voltage. So how do we get current from the drain to the source? Remember that in order to create some kind of charge flow or depletion region, when we had the MOS connection, we had to apply a voltage to the gate of a certain type. So what we do is we actually apply a voltage to the gate, which is exactly what we did in the previous lectures, and then we ground the other terminals. So we apply what we call VGS, So we apply a voltage, and what ends up happening is the holes in the p-type substrate move away from the oxide layer, just like it did with the MOS connection, and so we get a depletion region. And we also get an area in which electrons become attracted from one end to the other. So there's actually a channel of electrons. This is the N-type area that is created when you have the depletion region. So there is a channel that is created under that oxide layer just the same way as there was an N layer when we looked at the MOS device. This is the same thing. It's just a little bit differently applied. So this is a place where current can flow. And remember, current is opposite to electron flow. So the current, those arrows, those are standard or conventional current flow. Remember that when we turn the device and look at it in 3 dimensions, the current goes through that whole area. So it's not just a little tiny conduit it goes through. It's actually a whole big layer that the current will flow through. And that's why we can characterize the channel with the width and the length. And that determines basically the charge flow. In integrated circuits, the length is generally under a micrometer, and the width is under 100 micrometers. So they're very, very small. And this is one of the reasons why MOSFETs are really good in digital applications, because they can be made really, really, really small and still work. So the minimum voltage we need to create a channel is the threshold voltage. And the values typically for NMOS transistors about 0.3 to 1 volt. And then one other parameter that you need to know going into the next section is when we increase the gate to source voltage above the threshold voltage, which we can do. So we have a minimum value of VGS we need to create the channel. And then once we do that, we can go above it. That is known as the overdrive voltage. So that's whatever the difference is between VGS and the threshold voltage. We will pick right back up with this in the next lecture and talk about MOSFET operation.